in this class we will study about operational amplifiers. Okay, so operational amplifier, in short we can write it as op amps. Okay, so why it is known as operational amplifier? So operational means it can perform mathematical operations such as addition, subtraction, then integration, differentiation. Okay, so the mathematical operations can be performed by using operational amplifier. That is why it is known as operational amplifier. So many mathematical operations can be performed by using operational amplifier. So first of all, we will see its schematic symbol. Schematic symbol of this operational amplifier. Okay, so the schematic symbol for this operational amplifier, it is like this. This is V out, this is say V1, and this is V2. Okay, it is inverting input, and this is non-inverting input. So this is the schematic symbol of operational amplifier. Okay, and we can also write here it is plus VCC and here it is minus VEE. Okay, so VCC and VEE, plus VCC and minus VEE, these are the biasing voltages. Okay, so this is the schematic symbol of the operational amplifier. Okay, so operational amplifier has two inputs. First input is inverting input and the second input is non-inverting input, and it has one output. Okay, so this is the schematic symbol of operational amplifier. Okay, so an operational amplifier, it is a multi-stage. It is a multi-stage amplifier. Okay, it is a multi-stage amplifier. Okay, having very high input resistance, okay, very low output resistance, and coupling of multi-stage amplifier, coupling between different stages, it is used by using direct coupling. So because of use of direct coupling, it can amplify both DC and AC signals. So it is having very high bandwidth from 0 Hz to say 1 megahertz. Okay, so 0 Hz means DC signal. It can amplify DC as well as AC signals. Okay, and it has also very high gain. Okay, it is voltage gain. So these are the characteristics of any operational amplifier. Because of this very high input resistance and very low output resistance, it behaves as voltage controlled voltage source, VCVS. Because of very high input resistance and very low output resistance, it behaves as a voltage controlled voltage source. Okay, so these are the important characteristics of any operational amplifier. So we have seen the schematic symbol of operational amplifier, then we will see the circuit equivalent of operational amplifier. Suppose this is terminal 1, terminal 2, and this is negative and this is positive. Okay, this is VID, this is V1 and this is V2. Okay, and gain of the operational amplifier is A. Okay, so this is the equivalent circuit representation of operational amplifier. Okay, so in this circuit we are seeing that this is the input resistance. Okay, this is non-inverting input and this is inverting input. Okay, so terminal this one is V1 is applied to inverting input and this is non-inverting input. So an operational amplifier has two inputs. One is inverting input and the other is non-inverting input. Okay, and this is the Rin. Rin is the input resistance. Similarly, RO is the output resistance of this operational amplifier, and this is plus VCC and it is connected with, at this side it is minus VEE. Okay, so plus VCC and minus VEE, these are the biasing voltages. So this is the equivalent circuit representation of operational amplifier, and V out, this is the output voltage. Okay, so this is the equivalent circuit representation of the operational amplifier. And what is A? A is the open loop gain of this operational amplifier, and VID, this is VID. So how we can write VID? It is equal to V2 minus V1, V2 and minus V1. VID is differential input voltage. It is differential input voltage. Okay, so differential input voltage, it is represented by VID, which is equal to V2 minus V1. Okay, so V out, it will be equal to how much? It will be equal to A into VID. So it is equal to A multiplied with V2 minus V1. Okay, V2 minus V1 multiplied with A, it is the voltage, output voltage. Okay, so this is the equivalent circuit representation of operational amplifier, and in normal case A, it is approximately equal to 1 into 10 to the power 5. Okay, so the gain of operational amplifier A, it is the open loop gain of this operational amplifier, it is very high, because see, A is equal to 1 into 10 to the power 5. So if V2 minus V1, so if say V2 minus V1, if it is in the range of microvolt range, then also it can amplify it to A, it is 10 to the power 5 into 10 to the power minus 6. volt. So it is approximately equal to 10 to the power 5. So 10 to the power 5 multiplied with 10 to the power minus 6, it is equal to 10 to the power minus 1 volt. Okay, so it is in C, it is equal to 0.1 volt. Okay, so in the input side, if it is in microvolt range, then also we are getting in the output it is 0.1 volt. Okay, because of this A, high value of A, it amplifies with very weak signals also. Okay, then we can see about IC 741. 741 IC, it is basically 8-pin operational amplifier. Okay, so we will see the circuit diagram of IC 741. Okay, so it is a 8-pin IC. So this is pin 1, pin 2, pin number 3, pin number 4. This is pin number 5, pin number 6, pin number 7, and this is pin number 8. 1, 2, 3, 4, 5, 6, 7, 8. Like this. Okay, this is offset null and like this. This is inverting input and pin number 3 is non-inverting input. Pin number 4, it is minus VEE. Pin number 5, it is offset null. Pin number 6 is output pin. Pin number 7, it is plus VCC, and pin number 8, it is NC, means not connected. Okay, so this is the pin configuration of IC 741. IC 741, generally it is an 8-pin IC, and this is an operational amplifier, and this is the pin configuration diagram of IC 741. So pin number 1 and pin number 5, it is used for offset null, and pin number 2, it is inverting input. Pin number 3, it is used for non-inverting input. Pin number 4, here minus VE is applied, and pin number 7 plus VCC is applied. We can take output from pin number 6, and pin number 8, it is not connected. Okay, so what is the use of this offset null? Suppose this is V1 and this is V2. Even though V2 minus V1 it is equal to 0, then also we are getting output at terminals 6. Okay, so in order to null this output, we are applying some voltage to offset the output at 0 volt. Okay, so if this difference V2 minus V1, if it is equal to 0, then for ideal case its output should be 0, because it is 8 times VIT, so it should be equal to 0. But because of some manufacturing problem, some offset voltage may be there. So in order to cancel this and in order to reduce it to 0 volt, we are applying some voltage to null this output. Okay, so this is the use of offset null. Okay, and this is pin number 2, inverting input. Pin number 3, it is for non-inverting input. So inputs are applied to pin number 2 and pin number 3, and we are taking output from pin number 6. So this is the pin diagram configuration of IC 741. Then we will see the characteristics of of ideal operational amplifier. Okay, so we will see the characteristics of an ideal operational amplifier. First is voltage gain. Voltage gain, it is infinite. Voltage gain of an ideal operational amplifier, it is infinite. Second one is Rin, input resistance, it is infinite. Third one is R output, output resistance, it is 0. Fourth one is bandwidth, it is infinite. Fifth one is common mode rejection ratio. We will study later on about common mode rejection ratio, it is infinite. Sixth one is slew rate, it is also infinite. And the seventh one is perfectly matched. Perfectly matched. Okay, so these are the characteristics of an ideal operational amplifier. First is voltage gain is infinite. Okay, so R input it is infinite, R output it is 0. So because of this property, R input is infinite and R output is 0, it is also known as voltage controlled voltage source. Okay, bandwidth is infinite, so it can amplify both DC as well as AC signal. Okay, so from 0 Hz to up to infinity, it can amplify the signal without any attenuation. So it can amplify both DC as well as AC signal, because DC signal has 0 frequency. Okay, so it can amplify also DC as well as AC signal without any attenuation. Common mode rejection ratio, it is infinite. Okay, because of this property, noise signals are rejected. CMRR, it is common mode rejection ratio. So if it is infinity, means the noise or common mode signals will be rejected, and slew rate it is equal to infinity. Okay, for an ideal case. So what is slew rate? Slew rate is dV naught by dt, maximum value of dV naught by dt. So what is V naught? V naught is the output of the operational amplifier. Okay, so rate of change of output, it is the maximum rate of change of output. Okay, so what this signifies? Okay, so output should change simultaneously with the change in the input. Okay, so and it is perfectly matched. Okay, it should be perfectly matched. These are the ideal characteristics of any operational amplifier. We will now study about open loop configuration in operational amplifier. So basically we will be studying about 3 open loop configurations. In open loop configurations we will be studying about 3 configurations. First one is inverting mode, second one is non-inverting mode, and the third one is differential mode. Okay, so in any open loop operational amplifier, and this is say output. In any open loop configuration in an operational amplifier, we will be studying about three modes: inverting mode, non-inverting mode and differential mode. In open loop, V output, it is not connected with any of the input terminals, and in case of closed loop, the output terminal, it will be connected to either of the inputs, to either V1, to either V2 or to both. Okay, so this is the condition in case of closed loop. Okay, in closed loop, V output, it may be connected to V1, it may be connected to V2 or it may be connected to both. But in case of open loop, V output, this signal, it is not connected, it is not connected to either V1 or to V2 or to both. Okay, so this is the difference between open loop configuration and closed loop configuration. So in open loop configuration, we will be studying about these three modes. So first we will be studying about inverting mode. Okay, so the circuit diagram, it will look like this. The circuit diagram of an operational amplifier in inverting mode. In case of inverting mode, V output, it is equal to minus A into V1. How it is written like this? Okay, so in case of inverting mode, okay, open loop inverting mode, at the non-inverting input, this is non-inverting input, this terminal, it is connected to ground, and this inverting input terminal is connected to some input voltage. Say V in is the input and R1, this is the internal resistance of this voltage source. Okay, and we know that the input resistance of this operational amplifier is infinity for an idle case. For practical case, it is very high. So in comparison with the input resistance of operational amplifier, R1 is very less. So the voltage drop across R1, it is approximately equal to 0. So in that case, we can consider V in, it is equal to V1. Okay, so suppose A is the open loop gain of this operational amplifier. So V output, it is equal to A into V ID. What is ID? VID, it is A into V2 minus V1. So it is equal to A into V2 is 0 and V1 is, we can write V in or V1, both are same. So it is equal to minus A multiplied with V1. So this is the expression of V output in case of inverting mode. So if input signal is like this, then the output, it will be its phase angle, phase will be 180 degree, and it will be amplified. It will be amplified like this. It will be amplified, and phase angle it will be phase difference. It will be 180 degree. Okay. So this is all about inverting mode. Then we will study about non-inverting mode. In case of non-inverting mode, this inverting input, this is inverting input. Inverting input is connected to ground, whereas Vin is applied to non-inverting terminal. Non-inverting, this is non-inverting input terminal. Okay. So in case of non-inverting mode, the input signal Vin it is applied to non-inverting input terminal. See, Vin it is the input voltage source, and R2 is the internal resistance of this input voltage source. Because the input resistance of this operational amplifier it is very high. So in comparison with the very high input resistance, this resistance is very less. So the voltage drop across R2 it is almost equal to 0. So we can say that Vin it is equal to, suppose this is V2 and suppose this is V1. So Vin it is equal to V2. Why? Because the input resistance of the operational amplifier is very high. In ideal case it is infinite. So we can consider the voltage drop across R2 it is almost equal to 0. So in that case we can say that Vin it is equal to V2. So how we can write down the expression for V out? So we can write V out it is equal to A is the open loop gain of this operational amplifier, into V2 minus V1. Okay. So we can write it is equal to A. What is V2? V2 is Vin is equal to V2. So we can write V2 minus 0 volt, because it is connected to ground. So it is equal to A multiplied with V2. V2 and Vin both are same, because R2 is very less in comparison with the input resistance of the operational amplifier. So the voltage drop across this R2 is 0. So we can say that Vin is equal to V2. So this is the expression of output, V output, in case of non-inverting open loop configuration of an operational amplifier. Then we will see the third one. Third is differential mode. Differential mode open loop operational amplifier. So in this configuration or in this mode, circuit will look like this. See, this is Vin1, R1, this is R2, Vin2. Okay, suppose this is V1, this is V2, A, and this is RL, V out, and this is plus VCC, and this is minus VEE. Okay, so this is the circuit diagram for a differential mode open loop operational amplifier configuration. Okay, so how we can write or how we can express V output? V output, it is equal to A into V2 minus V1, where V2 is like this, V2 minus V1. Okay, so it is V2 minus V1, so it is equal to A V in 2 minus V in 1. Okay, so we can write like this, because R1 and R2 both are equal to 0. So this is the expression of V output in case of differential mode. Okay, now we can see in open loop configuration, A is approximately equal to 10 to the power 5. That is the open loop voltage gain. It is approximately equal to 10 to the power 5. Okay, so V output, it is equal to A multiplied with V2 minus V1. So it is equal to A multiplied with VID. So for a small input voltage, V output, we are getting a very high output voltage. Okay, now see, if VID, if it is equal to say in microvolt range, then V output, it will be in which range? It is equal to 10 to the power 5 multiplied with 10 to the power minus 6. So it will be it is in 0.1 volt, or it will be in the range of volt. So if in the input side, if VID, if it is in microvolt range, then it will be in V output, it will be in the range of volt. Okay, so let's see that for a small increase in input voltage, V output is very high. Okay, ideal voltage transfer curve. Okay, so ideal voltage transfer curve in case of open loop configuration, it is the graph between V output versus VID. Okay, this is minus V output SAT, which is less than minus VEE, and this is V output plus V output SAT, it is less than plus VCC. Okay, so and its slope, it is equal to A. Slope of this curve, it is equal to A. It is open loop gain. Okay, so in case of open loop configuration of an operational amplifier, if A is the open loop gain, then how we can draw the ideal voltage transfer curve? So ideal voltage transfer curve, it is the graph between VID. What is VID? VID is differential. It is differential input voltage. So for this type of circuit, this is minus the positive. This is inverting input and this is non-inverting input. This is V out. Okay, and it is plus VCC, and this is minus VEE. For this operational amplifier, this is open loop. open loop configuration. Okay, and A is the open loop gain of this operational amplifier. So the ideal voltage transfer curve, it looks like this. Okay, so we can see if VID is very small, in smaller range, it increases with the increase in VID. But after some time, if it reaches to V output saturation, okay, so in that case V output, this is V output, so V output, it is now flat, it is constant. Similarly for the negative side, it is constant after some increase in VID. Okay, so if V output, if it is reaches to minus V output sat, which is less than minus VE, then at that point we are seeing that the V output, it is almost flat. Now it is not changing. This is the maximum V sat, and this is the minimum V sat minus V output sat. Okay, so we can see that it cannot amplify the signal more than plus V output sat. Similarly, the output, it will saturate to plus minus V output sat. The operational amplifier in open loop configuration, the output, it will saturate to plus minus V output sat. Okay, so suppose if VID, if it is equal to say 10 volt, and here it is plus 15 volt and this is minus 15 volt. Okay, so if A is equal to 10 to the power 5, then V output, it is equal to A times VID. So it is equal to 10 to the power 5 multiplied with 10 to the 10. So it is equal to 10 to the power 6 volt. So this is not possible. It will saturate. V output, it will be equal to plus minus V output sat. This is the maximum limit. Maximum limit of V output is plus minus V output sat. It cannot go beyond this value, plus V output sat and minus V output sat. Okay, so this is the ideal voltage transfer curve of open loop operational amplifier.